Thank you. So hello, my name is Adrian, and I'm going to talk to you about potential architecture, big data architecture. So we, through the history of big data, we went from data warehouse to data lakes to lakehouse, and I'm going to present a new concept. The title is still we can debate the title and the name. So, Mirror Lakehouse. The goal is to make architectures which are faster, smarter, and better for big data. This title had, so first presentation for this presentation was presentation. The second one was data science plus data engineering equals love. Another one was turning the data lake, so the data swamp into wetland. So by planting trees in the swamp. Okay. So the elevator pitch is basically replacing the data layer. So with a semantic layer, meaning a machine model, a machine learning model. Instead of querying directly the data, we query the machine learning model. So how do we do that? First, we learn the underlying distribution of the data, the correlation in the data, not the data exactly. And that will allow us to query the data at monstrous speeds, because you're not working directly with terabytes of data, with just very small models. Capable of easy-to-use what-if type of scenarios. So once you have that model, you can ask it questions you don't necessarily have in the original data, but because you learn the correlations, you can query it directly. Of course, you can speed up queries by semantically compressing using the model. To explain a bit what that means, if you know the underlying distribution of the data, you can compress it to the absolute maximum, the theoretical maximum of your data. So you can even archive your data to its maximum potential. And of course, because we have GDPR and other regulatory requirements, we can safely share our data, not our data, but our models. So, how, more exactly? Okay, okay. So a little bit of introduction for probabilistical models for tabular data. When dealing with huge amounts of data, we don't need to actually query the data itself. We can have a small approximate representation of it. And data engineers know about data sketches, pre-aggregations, filtering, sorting. So this is known stuff. We already do that. This takes it to another level without actually without doing any kind of pre-aggregation, filtering, or sorting, just learning the model and query it directly. And of course, most of the time, most of our reports we don't even need, because 3 million points, I don't know, doesn't really matter. Sometimes you just need the overall picture, the relative data. So in this particular case, you just need a percentage, maybe, increase in sales or decrease in sales to 2 decimals. So there's lots of rich documentation in the research community, and it's called approximate query processing. So there's a lot of studies done on this. Okay, so this is the same thing. We want to make a model which is thousands of times smaller, like orders of magnitude smaller than the original data. And by doing this, we will reduce also the space, because you can delete the data. I truly believe that we don't need all the data that we are producing. Sometimes it's just superfluous. And we've seen presentations today about data swamps. And you can, even if you have the data, if you access only 30% of it, it's meaningless. And more than that, it's a liability, because GDPR and regulatory compliances. We reduce processing time, space, and resource usage at the cluster level is greatly reduced. As I said, lots of rich literature support. There's one very famous one from the Stanford group which made Apache Spark. It's called BlinkDB, which pre-samples tables in a hierarchical model. So you don't. What they do is they take at random a percentage of the data, for example, 10% or 20% or 30%, depending on your accuracy needs for that particular query. And it queries that data. It just basically takes 10% of your data and then runs the queries on that. BlinkDB was demonstrated that it's like 10 times, 20 times faster than Apache Spark by itself. The drawback is that BlinkDB it generates new data. Basically, when you sample it, it stores it in a hierarchical manner, but it has to do all the combinations between your data. If you have categorical data, you have to do every possible combination to get the full picture of your data. Otherwise, your accuracy drops. So you have to do a lot of samples, even though ultimately your query speed improves, but your storage grows exponentially. So another new, sorry for this, PM4DBs is probabilistical models for databases. Another new idea in the approximate query space is learning the probabilistical model. So there's one thing called BaseDB, which learns a Bayesian model. It's very good at making predictions. Just put your data in BaseDB, and it learns automatically, no data scientist involved. It's very good at doing missing data imputations, what-if scenarios, and even making predictions. The main drawback of BaseDB is you require a huge amount of computational resources, even for small data. It works, it's great, it's the holy grail. You can ask your database, not queries, you can ask it questions. But you can't really scale it to big data, so yeah. But the newest thing, so actually this is not the newest thing, is generative adversarial trees. So this is a model which trains decision trees, a very simple type of machine learning model. It's very simple and very small compared to the other models that we talked. So it was first introduced by Google Research at ICML in 2022. And it has several advantages. Really fast to build and have best performance of the machine learning models, including neural networks. So there's a lot of research that neural networks don't work that great for tabular data. They might work for sound, video, images, and the like. But for tabular data, it fails completely to very simple types of machine learning models. Of course, they are very easy to interpret, because you can see why the model took a specific decision. Again, great for regulatory compliances in the banking sector if you have to explain why you scored a client, you gave him a very low credit score. You have to explain why. So it's very easy to do that in this particular scenario. Yeah, and it's smaller than neural networks. Much, much smaller. Some examples on how it learns. This is a very typical data set, the iris data set. When people start learning data science, this is the first data set they look at. And it's basically a data set, 150 rows of a class of irises. And you can categorize those irises. So there's 3 types of irises in this data set. And you can characterize them by the petal length and by sepal dimensions and petal dimensions. So this is the starting point. We run the model. We learn, this is the tree. This is exactly the tree learned from that particular data set, just a small fraction of it. And can I point? No, I can't. I don't know if you can see, there's some nodes there. It includes sampling, and this tree demonstrates the relation between certain values in your data set, but not the exact. You can see there's a range. So for example, petal length between 1 and 3.15. It doesn't store the exact data, but you know that petal length is related to petal width in a particular manner for a particular range. So you just store ranges and the relationships between your features. And using this tree, you can just, how do you query? That's an important thing I don't think I'm explaining. You sample when you need the data. You want, for example, I want to know what is the average petal length for, I don't know, Setosa, which is a class, an iris class. And you go for here and you ask the model, give me examples of Setosa. And it will generate at random based on this, this particular tree. And it will generate as many data as you want, and then you can do your query exactly the same as you did before. Just do a select average group by. And it's guaranteed to give you a statistical relevant answer, which is close or near optimal to the original data. Okay, so this is what the model generates. For example, you go to the tree and say, generate me a proxy data set. So you do not touch the original data. The model generated this table, and it's unrelated. It's related by the model, but you generate the data on demand. And this allows you to put any SQL engine on top of it, be it Spark, be it whatever. So, practical considerations. Yes, you can make the models as big as you like. So, for example, you can train it to 100% accuracy. But that will defeat the purpose of actually using that model, because you can query the data alone, because the model contains connections in the data. So your model will be bigger than your initial data. So that's why we have to either limit some parameters of how big the model should be. And another practical consideration when deploying this is the thing that is, first time you install that, you have to train the models, and that will take a lot of time. But after this, there's just plug in and play. Yes. And thank you. Questions?
Can you hear me? Hello, thank you. Thank you for the presentation. In the iris data set you presented, it's a very clear data set where you have some input and some output data. So training the model is clear which are the columns which you use for input and which is the target. For a general tabular data set, how does this work?
This is a general data set. So you train your model not to predict something. You're trying to predict if the data is false or not. So you start by having the full data and then generating some random stuff that looks exactly like it, and then you train your model to detect if it's the real data or if it's the fake data. And doing this a couple of times, going back and forth, you eventually learn the whole data. So you don't learn to predict setosa, for example. You learn how to generate your full data.
So basically, you don't need to say these are the input columns and this is the output column. It's kind of determines the statistical properties so you can generate random data. Okay.
Yeah, so in the machine learning model, you just throw the table into the model and it will learn the table. You don't have to specify anything.
And are there any, I don't know, hyperparameters or stuff you need to configure during this training?
Yes. So there's a few things. Here, so the maximum depth of the trees and the maximum number of leaves. There's the primary hyperparameters of this type of model. And of course, computation time. So it can take a lot of time, and you can have a cutoff. You say, I want to stop after 3 hours.
All right, thank you.
No problem.
Any other questions?
Sorry, can you give us some examples of use cases?
Use cases. Every time a query is slow. For example, the exploratory data analysis. Every time you want to do that, you don't actually need the full data. You can just query a reflection of your data to say it like this.
Okay.
Reports which don't have, you don't need that much accuracy. You don't need all the precision that a float gives you, for example. What if scenarios? So you can ask, again, what is the average of the setosa? Or for example, you can do what if scenarios. You can ask, if I increase my sales by 50, if I increase my product by that amount, how would that affect my sales or my revenue? You could ask that question. Even though you don't have the data in the model will learn certain correlations of your data.
Okay. Any other follow-up question, or are we good to move on to the next one? Okay, thanks.
Hi. I was wondering if you try to put this model against any sort of anomaly detection, or if you can use the ranges for the decision tree that you mentioned.
You can,
for that use case.
Yes. As a use case, you can use this type of model for any type of ML type task. For example, anomaly detection. Sure, you can do that. Missing data imputation. So the original paper was exactly on anomaly detection and missing data imputation. You have some missing data and you want to fill in the blanks. For example, you don't have the age of a particular customer, but you can infer by the other whatever columns in your table or in your data set, you can infer a range of an age, for example. He's between 30 and 45.
Okay, thank you.
Are there any other questions? I think that's it.